Claudia, and thank you, the organizer, for the kind invitation. I'm going to talk about, I don't know why it's auto-playing. Okay. So I'm going to talk about some new two-sample tests. And here is a very brief outline. So I will first introduce the background and then discuss about the new tests. So basically, here is most simple setup in statistics. We have two samples, x1 to xn from one distribution, and y1 to yn from maybe another distribution. And our hypothesis is saying that these two distributions are the same, and the alternative is these two distributions are different. And this is arguably the most classical problem in statistics. And there are tons of literature for this problem. But even for this kind of simple problem, there are still some challenges in nowadays when the data dimension is high or when the data is even not Euclidean. And of course, like for high-dimensional data, non-Euclidean data, there are still a lot of existing methods for testing the equivalence of the two distributions. Most of them are based on some parametric models, and you can imagine that when the dimension is high, usually they need some strong assumptions on the model. Otherwise, the number of parameters will just explode. And here, in this talk, I'm focused on some non-parametric tests. So basically, people have been starting to extend one-dimensional non-parametric test to high dimension for a long time. And this one is actually the first practical method that can be used for whatever dimension. And here is an illustration plot. So here the data is in two dimensions. But you will see immediately that the method can be applied to whatever dimension. And this method was proposed by Jerry Friedman and Warren Zwarsky back in 1979, almost 40 years ago. And what they did is that when we have these two samples and they put them all together, and for example, for this kind of Euclidean data, we can use Euclidean distance or maybe some other distance, and they construct a minimum spanning tree. That is a tree that connects all observations with the summation of the distances of these edges minimized. And there is some very fast way of doing this, construct this minimum spanning tree on the data, essentially. And then they look at the number of edges connecting between these two samples. So representing here these red edges, so they are either like the connecting triangle to point, basically connecting between the two samples. And I will later just refer to this test as the edge count test. And the idea behind this is like that. So if these two samples are from the same distribution, then they would presumably be very well mixed, and then this count of edges connecting between these two samples will be relatively large. And on the other hand, if these two samples are from different distributions, then they are better separated. And then this number of edges connecting between these two samples will be relatively small. And so a small statistic, a small count, would support the alternative that they are from different distributions. So the idea is very simple. And surprisingly, this kind of simple test indeed have pretty decent power when dimension becomes large. So in their paper, they did some comparison with Hao-Chen t-square statistic. So they look at Gaussian data and only mean difference. And that will be the most simple setting for parametric models. And they compare their test with the Hao-Chen t-square test. And it turns out that when dimension is high, for example, like 50, 100, it's actually not that huge, like in that range. And then this test already has power higher than the Hao-Chen t-square test. So basically, even though this kind of test looks very simple, but when dimension increases, essentially those parametric tests, the power decreases so quickly that this test has its own niche there. And there are indeed some theoretical foundations for this kind of test. Actually, after 20 years almost 20 years after that test was proposed, and the work by Ma, Pearl and Bartowski, and they prove that for two multivariate distributions, and they are equivalent if and only if the distributions of the interpoint distance within each sample and between these two samples are all equivalent. And this gives some foundations for why this test might be make sense. And also a few years later, Hanzi and Penrose, they proved that for the test I just described, and if the minimum spanning tree is constructed based on the Euclidean distance, and this test is indeed consistent against any alternative, as long as these two distributions are continuous distribution in this multivariate, any two continuous multivariate distributions. And after Jerry Freeman and Ron Swarovski proposed this edge contest, later some other people follow up the work, and these two, Schilling and Hanzi, they both follow the earlier work, but actually they done this independently, and they extend this to k-nearest neighbor graph. And this is relatively simple to imagine, so I'm not showing a graph here. And actually, quite recently, in 2005, Paul Rosenbaum, he extended this test to some very interesting graph. So he called this test a cross match. And indeed, what he did is that basically we have these observations, and he paired them in a way such that the summation of the edges of all these, the summation of the distance between these pairs is minimized. And we can also call this minimum distance pairing. And later I will just refer to this as minimum distance pairing. And essentially, for this edge contest, it does not need to be limited to these graphs. So these are just some particular graphs people have been studying. And as essentially for this kind of test, as long as the graph represents some kind of similarity among the observations, it would do some job, basically. And this is the background. And I got interested in this test because it potentially could be useful for data in high dimension. And as we can see from here, essentially it does not need that the observations are Euclidean. So even for non-Euclidean observations, as long as we can define a distance on the sample space, this kind of test can be applied. And so I play around this test and then found some interesting phenomena. And this leads to the first part of the talk. So let's look at this toy example. So this example is very easy. So we have two samples from two distributions, and they are both multivariate normal distribution. And the first distribution is just the standard multivariate normal distribution. And the second one have mean mu and variance sigma square. And let's first consider the first scenario that sigma is basically 1, so the variance is the same, and only the mean is different. And the mean difference is essentially the L2 norm of the mu is only 1. And the second scenario that we still have the mean difference, in addition, the variance is also different. And let's think about these two scenarios. Which scenario would have higher power for the test we just discussed? Basically, for the first scenario, only the mean differs, and for the second scenario, in addition to the same amount of mean difference, the variance also differs. And things I mentioned is some interesting phenomena. You will get that it must be that the first scenario is doing better than the second scenario. Otherwise, it will not be that interesting, right? Because intuitively, the scenario 2 is basically it has more change. It should have higher power. But in reality, and so here I just set the sample size to be quite large, so it won't be the problem that the sample size is too small that causing this like weird phenomenon. And in most simulation runs, on this edge contest, just based on minimum spanning tree, it rejects almost every time for scenario 1, so power is almost 1. And it almost does not reject any time for scenario 2, so the power is almost 0. So it's not like a small difference. So the power in scenario 1 is almost 1, and the power in scenario 2 is almost 0. And so that this is in that.
Or alpha.
Alpha, yeah, alpha. Thank you. Yeah, but it's basically kind of like it does not have any power. Yes. And actually, it may be even less than alpha. Yes. So this is quite counterintuitive. When we first looking at this problem, basically, the scenario 1 is that
we have more noise in scenario 2.
Noise
is larger, power is decreasing.
But for this kind of test, remember that it does not mean it does not saying that it only detects for the mean. It's saying that so against for all alternatives. So the variance alternative is kind of like also like kind of signal in this case. So basically, you are mentioning a very good point. But basically, for their test, they are claiming that basically the test is consistent against all alternatives. So presumably, if the mean is the same, only the variance differs, they should also be able to detect a difference. And basically, here in scenario 2, that we have both a mean difference and variance difference, but they are not doing the work.
You check how much data you need for it to be, so because the theorem is correct.
Yes,
and
yes.
You need to have, at some point you will be able to detect them, right?
Yes, I'll come back to that pretty soon. Yeah. So essentially, it's a huge amount of data. And so basically, this comes because of the curse of dimensionality. So here, dimension is 100. It's actually not that huge. As you will see very soon, that this phenomenon occurs even for much lower dimension. For example, dimension is 20 or 30, something like that.
Just want to here how the mu's are chosen. Are they like uniform across all the coordinates, or are there like only a few sort of coordinates where you have a significant value and the rest of?
Actually, in this setup, it does not matter because it is actual. So every dimension is the same. So basically, you can set like 1.
Because you're taking Euclidean.
Yes. So because I'm taking Euclidean, so in this setup, everything is the same. Yeah. And let's just look at one typical simulation run for the second scenario. And so basically, just under this setup. And so here in total we have 2,000 observations, 1,000 in each sample. And in the minimum spanning tree, because it's connecting everything all together and it is a tree, so there are in total 999 edges in total in that minimum spanning tree. And if we look at the number of edges in the tree, so there are about 979 in this particular simulation run that is connecting observations between these two samples. And this is almost this is very close to its expectation. So its expectation is basically about 1,000. However, if we look at the within sample connections, so earlier we were looking at the edges connecting between these two samples. But we know this sample ID, so we can of course further look at the observations the edges connecting the observations within sample 1. And we can also check the edge connecting the observations within sample 2. And in this case, there are a lot of edges connecting within sample 1, and very few edges connecting within sample 2. And so basically, this is kind of like matching with the earlier intuition that we have these two different distributions, and if they are different, and the observations within the sample would be more likely to connect within the sample. And this is indeed the case. But basically, this so small number for the second sample make that this within sample connection to be much smaller, and also make this between sample edges to be too huge, and causing the test not powerful at all. And if we look at some statistics. So here we have these two samples, and let's say we have overall sample mean. And here this is plotting the distance to the center. So for all the observations in sample 1, we check its distance to the overall mean, and then its box plot looks like this. And for sample 2, it has basically further from the center. So basically, even though for these two distributions, they are different in both mean and variance, and because the mean difference is relatively small, so even though this relatively small amount is large enough for the test to perform very well if the variance are the same. However, the variance is actually a larger difference, and this makes these two distributions basically locates on these two layers, centered almost the same, even though the centers are slightly different, but they're almost the same. So we have this sample 1, it has a smaller variance, is in the inner layer, and the sample 2 has a larger variance, is in the outer layer. And because the dimension is relatively high here, and the points in the outer layer are more likely to connect to the points in the inner layer. And this causes this problem, basically. This is just a reflection of the curse of dimensionality. And refer back to how many points that we need so that the asymptotic result kicks in, as Debashis asked earlier. So let's think about this problem. So how many data points so basically in this problem, we have these two layers, the inner layer and the outer layer. And the problem becomes how many points we can place in the outer layer so that they would find themselves to be closer, rather than they find the inner layer to be closer. And we can reduce to think about this approximate problem, that how many points we can put on the surface of a D-ball such that no pair is closer to each other than to the center. So if this happens, that means they will find the center to be closer, then they will find any points in the inner layer to be closer. And this number can be approximated by this quantity. So essentially, we can just look at the unit ball, right? It could be any ball, and we just look at unit ball, and we can calculate the volume of the surface of the unit ball, and then divide by the volume of this dimension d-1 ball with radius 0.5. And so you can kind of think we have this surface of this unit ball, and we can place these balls with radius 0.5, and how many balls we can place there. That is approximately the number of points we can place on the surface of this D ball such that their pairwise distance are all larger than 1. And this number is in the order of 2 to the power d. So this is indeed exponential in d. And if we plot this number here, so this is the plot. And here the y-axis is in log scale. So for example, let's say when d is 100, we essentially need 10 to the power 30 points in the outer layer. Essentially, we can place a lot of like tremendous points there, and still they would find themselves to be further compared to the center. And for example, if d is 50, is about 10 to the 13, so that is 10 trillion. And so basically, with all those typical sample sizes like hundreds, thousands, even if 10,000, still like to be too small for them. Is like still too sparse for them. And let's say if even for d equals 20, it may be like 10 to the 7. So again, so basically like this kind of phenomenon already kicks in quite low dimension. And now the question is how to solve this problem. And of course, we can define, for example, new distance. So in this earlier problem, we can, for example, we can define distance as distance of these two observations to be the difference of the distance towards the overall mean. So that can be one distance. Then the sample x would be closer to each other because they are all to the center of almost that amount, and sample y would be also be together, and then this will solve the problem. But you can see very immediately that this is very application specific. So if we use this distance, then it won't work if we have these two distributions only differ in mean. Or if we have these two distributions and they differ in mean and differ in variance, and by the difference in variance, it might be different for different dimension, and then it would won't work as well. And so when I found this weird phenomenon, so I went to talk to Jerry Friedman, and then we have some discussion. And then we think we should find some new way of test statistic to make it work for all these scenarios. And so this boils down to what is a common pattern. Like, let's consider about these two scenarios. One is that this usual intuition, that is, we have these two samples from two distributions, and they are more likely to connect within the sample. And the other is this weird phenomenon that we have these two samples from two distributions, and for one sample, one is more likely to connecting within sample, and for the other sample, that is much less likely to connecting within sample. And if we describe these two scenarios, then we kind of see the solution. That is, basically, we just check these two within number of edges, edge count, two within edge counts, and then we compare with their expectations. And so before I introduce this test statistic, let's just have some notations. So here, in the following of the talk, I will just use G to denote this similarity graph. It could be the minimum spanning tree, it could be the nearest neighbor graph, it could be some other similarity graph you prefer. And let's just pull the observation all together and index them by 1 till big N. Big N is just the total sample size. And this GI is indicating a group ID, so GI equals 1 if observation is from sample 1, GI equals 2 if the observation from sample 2. And then the within the number of edges with connecting within sample 1 is basically we just go over all the edges in the graph, and that both end nodes are from sample 1. And R2 is basically the number of edges within sample Y, same story. And this method is totally non-parametric, so we use the permutation framework that later on all the probability, expectation, variance, covariance are based on permutation. And here is this new test statistic. So basically, this is in this quadratic form, and essentially, when here the sigma is the covariance of this R1, R2 vector, and we can see very clearly that if we define things in this way, then either direction of deviance from the expectation would contribute to this statistic. So basically, in this originally nice case that these two are very separated, and they are very likely to connect within each sample for both samples, and of course, this S will be quite large. And on the other hand, if one sample is more likely to connect in within the sample, and the other is much less likely, and this will also contribute a lot to this test statistic. And basically this would work for both scenarios. And for the expectation variance, indeed, we can compute compute them like in this nice analytical form. So you do not need to actually do permutations to get expectation variance in the earlier definition of the test statistic. And they are quite clean. So basically, it depends on the sample size, MN, and two characteristics of the graph. So here, the size of G is just the number of edges in the graph. And here, another quantity C here is the number of edge pairs that shares a common node in G. So as long as we have this symmetric graph, so it could be the minimum spanning tree, it could be some other graph. And as long as we have this graph, we count the number of edges in the graph, and then we count the number of edge pairs sharing a common node in the graph. And then the expectation variance can be obtained instantly. And let's check how the method, how the new test statistic works. So we think it works, but let's just double check. So let's look at the scale alternative. So that is only the mean is the same, only the variance different. And here we look at different dimensions, and the specific alternative is chosen so that these tests have moderate power, so we can compare them. And here data is just normal data, so we use normal data just because for normal data it is relatively easier for the parametric test and we all know normal data is the best, and you guys have some ideas when we show this plot, and you have idea like how strong the signal is. And here I'm also reporting the power of the Hao Chen t-square and based on the generalized likelihood ratio test. And in this table, this is showing the number of trials. Out of 100 trials that the significance level is less than 0.05. And so basically this number divided by 100 is the estimated power of the test. And you can see very clearly that when dimension is very low, like dimension is 2, then the test based on the generalized likelihood ratio test will be has the highest power. And of course, the Hao Chen t-square just done over here because it is not aiming for this problem. And however, when the dimension increases, it's actually not in large dimension at all. Like dimension equals 5, and this new test I'm denoting by S is already having a higher power than the generalized likelihood ratio test. And of course, when we make the dimension even higher, then it will be doing much better than the generalized likelihood ratio test. And you may see here that I have this 1,5 thing. So MST is just the minimum spanning tree, and MDP is the minimum distance pairing. And the 1 minimum spanning tree is just the minimum spanning tree. And 5 minimum spanning tree is actually a slightly denser graph. And in experiments, we found that if we make the graph slightly denser, it has higher power. This is intuitive. Basically, we are using slightly more information. And how is this 5 minimum spanning tree defined? So 5 minimum spanning tree is defined as a union of the first, second, third, fifth, and fourth and fifth minimum spanning tree. So the first minimum spanning tree is just the minimum spanning tree, and the second minimum spanning tree is a tree that connecting all the observations with summation of the distance of the in the edges minimized, subject to that it does not use any of the edges in the first minimum spanning tree. So basically, after we construct this first minimum spanning trees, we make all these edges that already in the first minimum spanning tree not possible for later on, and then we find the second minimum spanning tree, and then we find the third one. The third one is subject to the constraint that it does not use any of the edges in the first or second minimum spanning tree, and so on. And then this 5 minimum spanning tree is just a union of the first, second, and so on until 5th minimum spanning tree. So it is a denser graph and use more similarity information, and it works better. And so this is based on the scale alternative. And let's check how it works if only the mean changes. So basically, again, is this on the different dimensions, and the delta here is denoting the L2 distance between these two means. So the variance here is the same. And now, again, in the normal data, now we see that this is like a perfect scenario for Hao Chen t-square, and then its power is quite high. However, when the dimension becomes higher, then actually essentially the original edge-cone test is doing better. And of course, if we look at the new one, it's doing like similarly to the original one, but it's slightly worse than the earlier one. And they are better than the Hao Chen t-square. Mm-hmm.
Have you tried to compare this with sort of the energy statistic or kernel to sample tests?
So you mean like looking at this
pairwise distances, and then so like Gabor, Zeke, and then Arthur Greater means they have this kernel to sample tests.
So for the kernel to sample test, if we think about this problem, so for kernel to sample test, it's essentially like still have this closeness, and when dimension is very high, it still have that curse of dimensionality issue. And so this new test is essentially using like to some extent having a new angle, and it incorporates that into a statistic. And actually for this like normal kernel test, I don't know if there's any special one, but for the normal ones, it still does not incorporate these kind of problems here. Yes. And if both the location and the variance are different. For example, we can check this log normal data, so it's multivariate log normal data, and then because both the mean and variance are different, then we see that the new test is doing better. But basically, the new test is doing what we expect, and that is performance. And so we see that when the variance is different, then the new best is new. So let's say the new we call this generalized edge corner test, and earlier we referred to the original edge corner test. And so one way to look at that is if we plot the rejection region of these two tests, and here the x-axis is basically the centered R1, the centered number of edges within sample 1 R1 minus its expectation, and the y-axis is the centered R2. And for the original edge corner test, the rejection region is basically in this region here. And for the generalized edge corner test, the rejection region is basically outside this ellipsoid. And if there is only mean change, basically that's almost happen in this first quadrant. And then both tests have pretty decent power. However, the original one would have slightly higher power because it's kind of the rejection region looks like in this way. And on the other hand, in the weird phenomenon that one sample is more likely to connect within the sample and the other is less likely. So it happens in the second or the fourth quadrants. And then the original test would basically, in some special cases, it might still have some power, but most likely it does not have power. But for the generalized one, it picks up a power. So basically, that's one explanation of these two tests. And in the next few slides, I would like to talk about the asymptotics of the new test. So we proved that under some minor conditions that this test statistic converge to the chi-square distribution with degree freedom 2. And this makes the p-value this makes the test fast applicable, because otherwise we may still need to do some permutation to get the p-value. And indeed, these conditions are quite mild. So for example, we can show that if the graph is a k minimum span tree and k is of order 1, then and based on the Euclidean distance, all the conditions always hold, and then we have this asymptotic result. Let's just skip this. And so you may wonder that like earlier I talked about asymptotic results, like the earlier edge corner test is consistent against all alternatives, but we see that under many scenarios it does not work. So let's check here, like whether asymptotic kicks in early or late. So let's look at sample size quite small, so for example 50 here, and here is plotting the asymptotic p-value, approximate p-value based on doing 10,000 permutations minus the permutation. Excuse me, the approximate p-value is based on this asymptotic result, and this permutation p-value is based on 10,000 permutations. And we just look at differences, and we run 10,000 simulation runs under each scenario, and for different size of graph, one minimum span tree, 3 minimum span tree, and 5 minimum span tree, and in low dimension and slightly higher dimension. And we see that basically the asymptotic p-value is doing quite well here, just compared to the permutation p-value, even when the sample size is quite small. So of course, when we increase sample size, this will be doing better, and this is doing very well when the sample size, for example, 100 versus 200, something like that. And we can also see that if we make the graph slightly denser, then it's doing better. So basically, when we make the graph slightly denser, it has higher power, and it converges to the asymptotic distribution also faster. And so in the following, I would mainly focus on 5 minimum span tree. So I will need to see that what's the optimal case is still an open question, and we're still working on that. But just for practical purpose, 5 minimum span tree usually serves a pretty good job. So in the following, I will just use 5 minimum span tree for simplicity. And we can also prove the consistency of the test. But anyway, it's just some asymptotic result, and it does not mean that it will kick in very early. It's hard to check because there are so many different alternatives. It's not like under the norm that we can still do some checkings. And let's try to see how it applies to. This is just an illustration example of applying this method to some network data. And this network data, this is based on this mobile phone data collected by the MIT Media Lab. And what they did is that they gave 90 students and faculty and institute smartphones with the exchange that they can record everything. So I'm not meaning that they record all the contents, but they record like when they make the call, when they make the text each other. And this study was done back in 2004. So at that time, smartphone was something very fancy, and then people are willing to like exchange their privacy for the use of them. So you will imagine it's not possible these days. Like smartphone is almost a must. And of course, this data lasted for almost a year. So this data is quite rich, and there are a lot of questions we can ask. And one question of interest here, so we're under this two-sample framework, and so for example, we would like to test whether this phone call pattern within the weekdays and phone call pattern within weekends are the same or not. So basically, for each day, we can construct this phone call network with these nodes, these students and faculty, and an edge pointing from person A to person B if person A called person B on that particular day. So we have this more than 300 networks, and then among them, 236 are on weekdays and 94 are on weekends. And we would like to do some kind of two-sample test to test whether this phone call pattern differs between the weekdays and the weekends. And this kind of reflects their friendship among these people. And so here we just use a 5 minimum spanning tree and connect on this in total 330 phone call networks. And here we just try some very easy distance. So of course you can propose some other distance, and here is very easy one. So the distance is defined for two networks on day S and day T. It defined as the number of different calls divided by the square root of number of calls on day S times the number of calls on day T. So it's a very simple distance. And we see that in the for the original test, the p-value is relatively large, it's 0.37. And for the generalized edge count test, the p-value is quite small, it's 0.04. And of course, there is no ground truth, and we don't know which one is indeed telling the story. And so let's just dig into the statistics to try to understand. And so here we have this 5 minimum spanning tree, and in total we have 330 networks. So in total there are 5 times 329 edges in the graph. And among them, 663 are between sample edges, and 814 are edges connecting within weekdays, and 168 edges connecting within weekends. So of course this is much larger because there are much more weekdays than weekends. And we compute their expectations. So for the between sample edges, expectation is 673. And this is not too much larger than this original, what we observe. So recall that for R0, the intuition is like, if this R0 is small, that means that these two samples are better separated. So small R0 indicates alternative. And so indeed, this is smaller, but after we standardize by its standard deviation, then it's not as significant at all. So it's like 0.03, so negative 0.03. So the p-value corresponds to the p-value 0.37. And then let's look at the other tools. The two within sample edges. So first of all, let's look at for sample 1. So now we see that the observation is relatively smaller than its expectation here. And so again, go back to the earlier intuition that the first intuition for the original test, that is when these two are different, then within each sample they will be more likely to connect. But at least this is not the case here. So at least here for sample 1 is like slightly less likely to connect within the sample. Even though it's not that like huge difference, but it's still slightly less likely to connect within the sample. And for sample 2, then it is kind of like match the intuition that is more likely to connect within the sample. And so basically combine things all together. So one explanation is that so basically we like weekends, like you can imagine like weekends when you call other people is more like personal relationship. But for weekdays, like you need a lot of work to do. So it's more like professional like relationship. And so this is saying that the personal relationship is like you can kind of like analogy is that like has a smaller variance, and the professional relationship has a larger variance. So this is quite a match with our intuition. So personal relationship is more stable and it's like has a smaller variance. And for professional relationship, of course, you need some work to do, and then you have to connect to someone, and then it will be like so you will have larger variance. And this is indeed the case. And for the new statistic, it basically combined these two informations all together. For the original one, one is less and one is larger. They cancel out with each other, and it becomes not significant. But indeed, this both information should be incorporated together. And then in the new test, it picks this signal, and then indeed that these two samples are indeed quite different. So basically, that's all for the first part. Any questions? Or maybe we can reserve for the second one, because everything things are very closely related. Okay, so now let's revisit the earlier power table we've seen before. So this is the power table we've seen that we have different dimensions, and only the mean differs. So here delta is the L2 distance of these two means. And we see that here that this original test has a higher power, the highest power when dimension is high. And of course, the new test, the power is also quite decent. So this kind of like leads to the conclusion that probably like if we want to use this test, if we are uncertain about the alternative, then we probably would recommend to use S. But if we only concerned about the mean change, like if the variance change we don't care at all, we only want to detect mean change, then probably we will still want to stick with the original test. And then when we explore things a little bit, then we find something very interesting. So let's look at another toy example. So here the setup is even simpler than the earlier one. So again, the first sample from the standard normal multivariate number distribution, and the second one only the mean differs, variance is still the same. So it's even simpler setup. And the mean difference is set to be just 1.3, just to make these two scenarios have multiple power to be comparable. And dimension here is just 50. And in scenario 1, these two samples, they both have 50 observations. And in scenario 2, the first sample again has 50 observations, and in the second sample it has more observations. It doubles the observation. It has 100 observations. And which scenario has higher power for the original test? So since I asked this question, you might think there must be some weird conclusion, right? So even though when we look at this, it seems like the scenario 2 has more observations, and presumably usually has higher power. But since I asked question, that must mean that scenario 1 has higher power. And that's indeed the case. So here is basically plotting the power on different minimum span trees. So as we briefly discussed earlier, so usually we would recommend to have 5 minimum span tree, and because this usually has like higher, it's like a big jump from the 1 minimum span tree. And here these circles are the power of the scenario 1. So on the different choice of case, k minimum span tree, and this is the power, estimated power. And these dots are scenario 2. So when we increase the number of observations, the power decrease. Actually, except for 1 minimum span tree. But in reality, we are not recommended to use one minimum span tree because it usually has a lower power. And so if we, for example, if we want to use 5 minimum span tree, then this means that we increase sample size, then this makes the test has lower power. That means even if we are under the second scenario, we have more observations for the second sample, we probably only want to use 50 of them in the test. Otherwise, this will make the test has lower power, and we definitely don't want something like that, right? And so let's try to explore what happens. So here, this is based on 1,000 simulation rounds, and it's just based on 5 minimum span tree. And here, these two box plots are plotting the difference. So here, R is the original test of statistics, is the between sample edge count. And we are looking at expectation. Its expectation minus its itself. So recall that on the alternative, R should be less than its expectation. And so the difference should be positive. And in both scenarios, so D1 is basically this box plot of the difference on the 1,000 simulation rounds for the scenario 1, and D2 is for scenario 2. And indeed, most of the time they are positive, and seeing that indeed there is some signal there. Of course, the signal, because we set up, under this setup, the signal is quite weak. So under sometimes, indeed, for that 50 observations, there's basically no signal at all. And we can see from here that scenario 2 indeed has a larger difference compared to scenario 1. And that is matches with our intuition because we have more observations. It should have a slightly stronger signal. And that is indeed the case. But what makes it not working? And this comes from this standard deviation. So here is plotting the standard deviation on these two scenarios. And for scenario 1, standard deviation is almost around 10. And for scenario 2, the standard deviation is almost around almost 20, like maybe 19, like 1.9 times the standard deviation of the first time. So of course, when the sample size increases, we would expect the standard deviation to increase a little bit. But here, like for the first scenario, the total sample size is 100. For the second scenario, the total sample size is 150. And if we take the square root of 1.5, it's probably 1.2 something, and it's much smaller than this 1.9. So this is a huge jump here. And indeed, the problem is caused by this variance boosting problem. So if we look at the variance expression of this between sample edge count, and it has a multiplier, and then this is the number of edges in the graph, and then we have the second term here. So the last term is almost negligible. So for example, in the k-minimum span tree, number of edges in the graph is of order n's, and this is just some constants. And for the second one, let's take a look. So here, GI is denoting a subgraph inside the whole graph that connects to node I. And so the size of GI is basically degree of node I. And this is a summation of degree squares. And this quantity can be quite huge. So for example, if we just, this is based on one simulation run, and this is a typical simulation run. And for k minimum span tree, here these circles are the size of G, so of course it's linear in K because it's K minimum span tree. And these dots are the quantity of the second term. So this increase dramatically and as the K increases. And when these two sample sizes are the same, m equals n, then this term almost vanishes because this becomes negative, and this makes this even smaller. But as long as this m and n, they are not the same, or let's say they are of the same scale, but the difference is of the same scale of them, then this term can be huge. It's basically dominating this variance. And this causes so even though the mean difference also increases when the sample size increase, but the variance is increased so fast that makes overall signal to be decreased. And then how to fix this problem? So we can see from earlier that there's nothing particular about this R0. So R0 is just some statistic, and we do not need to stick with this R0. And earlier we use this quadratic term of R1 and R2. And here we can use some other forms of R1 and R2 as well. And indeed, we propose to use this one, this weighted form. And here, P is basically the proportion of observations in sample 1. So m here denoting the number of observations in sample 1, and n here denoting the number of observations in sample 2. And so here p is basically the proportion of sample 1, and q is basically the proportion of sample 2. And so basically, these R1 and R2 are inversely weighted by their sample size. And this is kind of intuitive. So basically, if we have these two samples, and one sample has a much larger sample size, and another has much smaller sample size, you can kind of think like it will be much easier to form edges within a sample with a larger sample size. And of course, some kind of difference here will be also kind of like, so even the same amount of difference, for example, like in the earlier problem, the network problem. So because of weekdays, there are much more weekdays, and so it differs from its mean, like in that amount. And for weekend, it even differ in the same amount. That same amount should has higher weight, and that's basically the idea of here. And indeed, if RW is defined in this way, it has the smallest variance among the form of this linear form of R1 and R2. And we can also show that the variance of RW defined in this form is bounded by this. And we just totally get rid of this dominating term that we dislike. And then this totally solves this variance boosting problem. And this is the result. So we've already saw partial of the plot earlier. So these dots, these circles are the original test, scenario 1. M equals n equals 50, and these dots are the original test, and the second scenario, m equals 50, n equals 100. And so for this form, if these two sample sizes are the same, then this is totally equivalent to the original test. And it only differs with the original test when these two sample sizes are different. And so on the first scenario, that these two samples have the same observations, then it's totally the same here, these circles. And under the second scenario, that we have different observations, different number of observations, then it differs from the original test. So these dots are the original test, and these blue triangles are based on this RW. And now it matches with our intuition that, so we can compare them with these circles, and when we increase the sample size, the power of the test increases. And that is what we want. And that is what the Prof test should work. And here I'm also plotting the power of the generalized edge contest we discussed earlier, this S, the quadratic term. And for S, so because here this is only the mean difference, so S is indeed doing slightly worse than the original edge contest. So this green squares are the power of S, so it will be lower than these circles here. So because it's only the mean difference, and if the sample size are different, then these are those solid squares. And again, this is worse than this based on the RW. So basically, everything not match with our intuition, and that's kind of some test that we would like to use. And these are some other simulations under some different distributions, different dimensions, and we all see this kind of pattern. And again, under some mild condition of graph, actually this conditions are even milder than the earlier one. Then we can show that the standardized version of the weighted edge contest according to the standard normal distribution. And again, we can check. Because these are milder than the earlier one, so the K-minimum tree automatically follow these conditions. Like these conditions always hold for them, and we can also prove consistency. And I'm just don't want to run into that. And we can check like how quick this asymptotic kicks in. And indeed, when the sample size are quite small, like the asymptotic p-value is almost very close to the permutation p-value. So basically, the asymptotic kicks in very quickly. It kicks in very small sample sizes. It's not like in these trillion sample sizes. It's like just 25, 50, 50, 100, a very small sample size. And let's revisit this network problem. So we have seen this before. And now let's see like how this weighted one works. So here earlier that we have this R1, sample 1 is the networks on the weekdays, and sample 2 is the networks on weekends. And we've seen earlier that these networks on weekends are more likely to connect within each other, and the networks on weekdays, they are slightly less likely to connect within themselves. And S, of course, combine these two information all together, and it works quite well. And for RW, so because it has a weighted version, and here, so let's look at difference. So difference here is like 36, and here the difference is like negative 26. So in the original one, they just add up together and they totally cancel out the signal. And for RW, because we have, now this is down-weighted, and this is like relatively higher weighted. And then the difference is like let's say like 22, something like 22. And it's much larger than the difference here is like almost 9. And what's more is that here we're also reporting the standard deviation. So because of the variance reducing effect in terms of designing this weighted statistic, the standard deviation is much smaller. And then this results like we could pick up the signal here. And so just wrap up. So we discussed these two new edge count tests, and to address the problems in this original edge count test, so that it can account for more types of alternatives, and it could work properly for unequal sample sizes. And so I've mentioned multiple times that this test can be applied to data in any dimension or non-Euclidean data, as long as some distance can be defined on the sample space. And if you want to capture like all kinds of alternatives, then probably the generalized edge count test, the quadratic term, would be recommended. But if you are quite certain that the difference is only in mean, and you only want to pick up this mean difference, then probably this weighted edge count is recommended. So it's kind of like the generalized likelihood ratio test versus the Hotelian t-square test, something like that in that flavor. And all the tests are included in this package called G-test, short for graph-based tests. And you're more than welcome to download this package to try. So if you have some samples and you want to just take a look, and this can be something you can try very initially, because you do not need to have a very good understanding of data. As long as you can kind of tell like some observations are closer, some observations are further, then you can try this test. And these are just all the references. And thank you for your attention.
Yeah, thank you very much. I think we may have time for questions.
Any of this weighted edge count, so the issue that you mentioned, I mean, you explained very nicely, is that when M and N are of different sizes, then with the other tests are different. So I'm just wondering, so did you check like if there is kind of a point where if the order of M and N are really different, like say N is M to the power 1.5, something like that, what will happen to this test? I mean,
that's a very good point. So essentially, for all these like asymptotic order things, we assume that M and N are of the same order. Yes.
Yeah, sure. So for the asymptotic, but I mean, in practice, I understand. But suppose, I mean, I'm just saying that if you do some kind of study of that, and then question is two things. One is that whether there is a way of fixing that, and also just what happens, right?
So from my experience, so for example, like let's say 5 versus 200 or 5 versus like 300, it still works.
Mm-hmm.
So it may not work. So of course we would need a slightly higher signal to have them have equal power. So with the same signal strength, then we will have lower power, but still it works. But for the original test, it will definitely fail.
It's a very interesting talk, but for practical implementation, have you thought of just using a subsampling to implement your test? And if you have thought about what is the general guideline, what should be the sample size for that?
That's a very good point. So we haven't done in this direction, but I would imagine like for this test, you can subsample with, let's say, those general subsampling procedures, and you can fit into this like quite easily, right? So we can have these two samples like of a smaller sample size, and since these two tests do not require a large sample size. So for example, you can subsample, for example, like 50-50, and then I think that's actually a pretty good point. So I was like having trouble with some scenario that if these two distributions, they are like maybe like mixtures of distributions, and then maybe either like these two scenarios fits the data. So it could be some mixture, and it's hard to say. And the subsampling could be one good solution, because then we can look at like those like more local features, and it may pick up these things. So that's definitely something like I think I will explore. Thank you.
Yeah, so maybe let me just ask a quick question. So from the simulation point of view, you have only looked at mean changes and variance changes, right?
Mm-hmm.
I mean, okay, the problem is obviously very general, and you can look at
Yes.
anything,
Yes.
but have you thought about other things that may be reasonable and that for which the thing may be good or not so good?
Yeah, that's also a very good point. So here, just for simplicity, I just use these simple examples. But indeed, we try something like much more complicated. So for example, let's say these two distributions, the variance in this like structure of like one row square, and so on, like something like that. And if row like differs, like these tests usually have pretty good power in detecting that as well. And we also tried, for example, like variance like so one is in also some like fake example, like one is in decreasing like variance for different dimension, one is in increasing, and it also works quite well. So we tried many scenarios, and indeed it's not like, so of course in this talk I just want to make things simple, and all the examples are like just the simple ones, but indeed we try many others, and they usually work pretty like surprisingly good. Yes. Yeah. Thank you.
Thank you. If there are no urgent questions anymore, I would like to make a short announcement, and then thank you again. So just I would like to mention that the two talks today of Alexander Auer and Debashi Powell have been switched. So Alexander Auer is going to give the talk after the coffee break. And now let me thank you again.